Hello there. Today I'm going to finish actually. The discussions have started on counting distributions, okay? And the last topic is going to be on the number of different ways to distribute n identical objects to k identical boxes. But now, before I dive into that, I want to mention basic facts, for example, facts like what is common in all the counting, all the distributions we have counted, and what makes one different from the other. Okay, what makes one different from the other? That's what I'm going to. First, let me list all the kinds of countings we have done. First one was the distribution of, okay, we put this one here, and distinct items into k identical boxes. And then we have done n distinct items into k distinct boxes. Okay? Then we did n identical objects into k distinct boxes. And today, okay, this is for today, we are going to do n identical objects into k identical boxes. Okay? Now, what do all this have in common? First question. What do all have in common? Okay? So, what happens is, this is our approach. Okay? We have n objects here. Whether they are distinct or not, we do have k boxes to receive them. So, here we have k boxes. It doesn't matter whether they are distinct or not. Now, what happens is, we have to divide this into this n objects into parts, into k parts. So divide the n objects into k groups or parts, okay? K groups, so that a group goes to a box. Each group goes to a box. A part or a group goes to a box. So, what makes one distribution different from the other is basically the sizes of the boxes, the k boxes. The sizes of the k boxes put together should be different from other sizes of the k boxes to make those two distributions different. Okay? So, what matters here is, what matters in all cases is the sizes of the parts in a distribution. Okay? One set of sizes different from another set of sizes will make different distributions. Now, what happens when we add one more property, like the objects, the n objects are distinct, okay? So, we are going to discuss now what makes them different. What makes one different from the others or from the rest? Well, if the n objects are distinct, then composition matters. Decompositions of the parts matter. Okay, the compositions of the parts matter. For example, let me give you this example. Suppose I have n to be 4 objects to be distributed into 2, okay, into 2 parts. Now, this distribution, let's say 1, 2, and 3, and here we have 4. While here we have 1, 2, 4, and 3 there. See, these two distributions are different. I mean, of course, I'm abusing this notation, but you would understand, right? So, you see, this distribution is different from this one because here, one of the boxes has 1, 2, 3, while here, one of the boxes has 1, 2, 4. Or you can as well say, this has 4 separately in one box, while this one has 3. So, the way the n objects are combined, or the way we combine some of the objects of the n distinct objects to be part of, or to be in a box, or to be in the same part, matters. That matters because of the fact that n objects are distinct. Now another property of these distributions, which makes one, those different, one different from the other, is the K boxes are, if the boxes are distinct. Okay? If the boxes are distinct, then order matters. What does order mean? Then order matters. What does order mean? Which part goes to which box matters. Okay? Which part goes to which box matters. So for example, I have 1, 2 there, or 1, 2, 3, and 4, as in the first one. But now, since the boxes are distinct, let's call this A and call this B. They are distinguishable. And actually, when we put 4 there, and 1, 2, 3 here, of course, the compositions are the same. 1, 2, and 3 are together, 4 is alone. The same thing happens here. But, since the boxes are distinct, A contains 1, 2, 3 here, but here it has 4. So you see, which part goes to which box matters, means this. So these two are considered to be distinct. These two are considered to be different distributions. Okay, so now you have some basic idea on why we have been saying all this time distinct objects, distinct box, identical objects, identical box, and so on. It's because of those two factors, the composition and the order of the boxes, or where a part goes, which box gets which part, matter, and the numbers differ accordingly. Very good. Now, when you come to today's topic, well, it's a distribution where neither composition nor order of boxes matter. Okay? Yeah? This is the number of distributions of n identical objects into k identical boxes. Okay? So here, neither compositions nor order of boxes matter. All that matter here is the number of the sizes, okay, in a distribution. So this has something to do, this would lead us to relate such a distribution to what we call partition of integers, partition of positive integers, particular, okay? So here, all that matters in this counting is the sizes of the parts in a distribution, in each distribution actually. Okay? So, let me introduce first one important item here because this partitions of positive integer are already counted. Okay? So we can make use of that in order to count the distribution. As usual, a one-to-one correspondence could be established so that we can make use of those numbers, those low numbers actually, though difficult to compute. Okay, so definition, a partition of a positive integer. I'm interested in that, in this particular case, positive integer n is just, I can take it as a list of numbers or I can take it as an expression, okay? An expression of n, okay, positive integer n into k parts. That I am interested in that, into k parts, sorry for this, is an expression of n as the sum of k positive integers. Positive integers. And notation we use for that, the notation we use is P and K. This stands for number of partitions of n into k parts. Okay? Into k parts. For example, let's see. For example, take n to be 6 and k to be 3. Okay, how many different ways can I partition integer n, 6, which is 6, into 3 parts? You know that 6 is 1 plus 1 plus 1 plus 1. So it's as if I'm distributing the ones into the 3 boxes so that each box has something that adds up to, I mean, all the boxes have numbers that add up, positive numbers that add up to 6. Okay, so in this case, 6 into 3 parts, okay? Obviously, I've said k positive integers, so 0 is not allowed. 0 is not allowed. So I can write 6 as 4 plus 1 plus 1, or I can write it as 3 plus 2 plus 1, or I can write it as 2 plus 2 plus 2. I don't think there is another way of writing it. So P of 6, 3 is nothing but 3. Okay? P of 6, 3 is 3. What does this count, or where does this take me to my distribution problem? Distribution of identical objects to identical boxes. Well, as you can see here, I should have actually mentioned it in the definition, I'm sorry. Order does not matter. Order does not matter. See, it's an expression which gives us 6, okay, as a sum of 3 or k positive integers where order is not considered at all. So, 4 plus 1 plus 1 is a partition, as 1 plus 4 plus 1 is a partition, or 1 plus 1 plus 4 is a partition, or those three partitions are considered to be 1. So, when we add it as a remark or as a note, note that order does not matter in a partition of n, in the definition of a partition of n. 4 plus 1 is as well this one is 1 plus 1 plus 4. There are only 3 permutations of this. All of them are just 3 of them are counted as 1. And only 1. Okay? They are not 3, they are 1. That's what I mean. So, you see, this goes along, or it gets along with the fact that our distribution, in our distribution, the K boxes are identical. Order does not matter. Which part goes to which box doesn't matter. Good. Therefore, you see, given a distribution here, given 6, which is 4 plus 1 plus 1, there corresponds a distribution. A distribution of 6 identical items into 3 identical boxes. Now, well, I'm going to put 4 in here, 1 in there, and 1 in there. But obviously, since 0 is not a part, none of these boxes is empty. So I have no empty box here. Again, given this distribution, where there is no empty box, I can simply express 6 as 4 plus 1 plus 1. Okay? It doesn't matter, as I told you, it can be 1 plus 4 plus 1, 1 plus 1 plus 4. There is no difference. It's a single partition of 6 by definition. Therefore, from the partition of the integer, I got a distribution where none of the boxes is empty. From a distribution where none of the boxes is empty, it is straightforward to determine a partition of 6 into 3. That is where the partition number of the number of partitions of n into k parts will lend us a hand in solving this problem. So, if you take this notation, P and K as the number of I think I have already introduced that, the number of partitions of n into k parts, positive integers, integers, counts, can count the numbers, distributions of n identical objects into k identical boxes where none of the boxes is empty. Is empty. So P and K can count, in particular, those distributions of n identical items into K identical boxes where none of the boxes is empty, but we need to count those distributions with empty boxes too, okay? With some of the boxes empty. So what do? Let's go back to our example, okay, of 6. Now, I can express 6 as, actually, let me ignore the definition of partitions or the fact that 0 is not a part of such a partition. But let me write 6 as 6 plus 0 plus 0 because it corresponds to a distribution of identical items into K boxes where some of the boxes are empty. Okay? So this corresponds to, okay, 6 items are, all the 6 items are here, but these are empty. These are empty. Remember, we have used the same idea while using Stirling numbers of the second kind. Then I can express this as, okay, 5 plus 1 plus 0. Okay, here I have 5 objects there, 1 there, and this is empty. I can express this as 4 plus 2 plus 0. Okay, so I have 4 there, 2 there, and leaving this empty. Okay, so 3, or I can write 4 plus 1 plus 1. Okay, this is 1, which is as well a partition of 6. 3 plus 2 plus 1, and actually 2 plus 2 plus 2. Now, of course, this 3 can be counted by P6, 3. There are 3 partitions of the number 6 into 3 parts. Okay? Now, how am I going to view those? Okay, let me consider those 2. Okay, they are not partitions of 6 into 3 parts, but I can take them to be partitions of 6 into 2 parts. Okay? Into 2 parts. So, there are 2 partitions of 6 into 2 parts. Actually, 1 is missing. I can see that 1 is missing because 3 plus 0 is missing 2. So I am sorry, but I have to add that. 3 plus 0. So you see, I have 5 plus 1, 4 plus 2, 3 plus 3. There are 3 partitions of 6 into 2 parts. So I can count that to be P of 6, 2. Okay? We have 3 there, we have 3 here. And if you consider this one, I can consider it as the number of a partition of 6 into 1 part, and I can count it using the partition number 6 into 1 part. Now, you see, we have added, we have expressed 6 as a sum of 3 numbers, where some of them could be allowed to be zeros, and you have seen how we have counted or how we have made use of the partition number into K, of n into K, to count even those distributions having empty boxes or involving empty boxes. Therefore, what happened here? What happened here is the number of distributions, now I can count, number of distributions of n identical objects into K identical boxes. That is given by the sum j varying from 1 to K of P and J. This is because we have added P61 plus P62, which is 3, plus P63, which is 3, P61 plus P62 plus P63 has given us the number of distributions of 6 identical objects into 3 identical boxes. Here we don't need to add the condition that no box should remain empty. Of course it can remain empty and we can count it using the partition number of n into k parts. Okay, into k parts this way. But you see, it's a bit, especially when the n's and k's large, when n is large, the difference between the two is large, then the computation of these numbers gets a bit uglier. So probably a couple of formulas to reduce, you see, the size of n, so that it gets closer to the k, and becomes easier to compute. I need to introduce some recursive formulas, okay? Recursive formulas. But the idea of the formula is this. We are dealing with, okay, let's consider a distribution. Actually, it's a distribution. It's not unique, actually. A distribution of n identical items into k identical boxes. Now we have these k boxes, where I need it, or it's important that no box is empty after a distribution, because I need the n to count this distribution. Now you see, one way to guarantee that no box remains empty is to give each box a 1. Okay, one of the objects, they are identical objects. So just putting an item in each box, that makes it, that guarantees the distribution not to leave a single box empty. Therefore, once I have distributed this into k boxes, okay, I'll be left with n minus k objects to be distributed. Distributed into the k boxes. Now you see, I'm free. I'm free to distribute the remaining n minus k objects to a single box, to 2 boxes, to 3 boxes, or to all the k boxes, because there is no risk that a single box remains empty after a distribution. So, you see, there is a one-to-one correspondence between this distribution of n minus k objects into k, okay, and the number of ways to distribute n identical objects into k where none of the boxes remains empty. None of the boxes remains empty. Therefore, the number of ways n identical objects could be distributed into K identical boxes is given by, or could be given by, the sum of Pn minus Kj, where j varies from 1 to k. You see, I have finished my k of the items. I have utilized the k just to make sure that none of the boxes is empty. So now I'm left with n minus k. Now I'm free to distribute this in any way so that I can make use of the P formula, the P and K formula to count the distributions. Okay, I'll consider distributing the n minus k to 1 and only one box. Then I will have, I can count it. See, one box, nothing. Of course, it's going to be empty. I will have the n minus k 1. Then two boxes where, then it will be Pn minus k2 and so on and so forth. And that will count the number of distributions of the n items into the k boxes. Now, this is Pn, right? This is exactly the same as Pnk. Pnk. By the same reasoning, I can do that to a preceding term, this is Pnk. I can do the same to Pn minus 1, k minus 1 too. The difference is exactly n minus k. If I give k of this into, k minus 1 of this into this k minus 1 boxes, I will be left with n minus k objects. So by the same reasoning, follows that n minus 1. This is exactly equal to, again, j equals to 1 to k minus 1 this time of p n minus k j. Now, putting those two together, this is 1 and 2. Now, putting those two together, those two relations together, we have, okay, let me start with this one. P and k is equal to, okay, the sum j varying from 1 to k minus 1. I will just write the case term separately. K minus 1, p n minus kj plus, of course, when this is k, we have p n minus k n minus kk. Okay? Now, we've said by number 2, by relation number 2, we've said that this is nothing but p of n minus 1, k minus 1. So this will allow p and k to be evaluated using its preceding term, p n minus 1, k minus 1. It's a recursive formula. So there are, p n k is nothing but p n minus 1, k minus 1 plus p n minus k k. P n minus k is reduced, because n and k are reduced by 1 there, and here a lot. So let's see an example. Example of what we have already seen. Case 3. Now P6, 3 is equal to P5, 2, P5, 2 plus P6 minus 3 is 3, 3, 3. K is 3. Okay? In how many different ways can we partition 3 into 3 parts? Just ask 1 plus 1 plus 1. That's only one, and there is only one way to partition n into n parts. Okay, so this is simply 1. In how many ways can we partition 5 into 2 parts? We have seen 5 can be given as 4 plus 1 or 3 plus 2. What else? Nothing. Partition. You see, order does not matter, so it's either 4 plus 1, 3 plus 2. 2 plus 3 is the same as 3 plus 2. Therefore, this is 2. Okay? So what this means is P63 is nothing but 2 plus 1, which is 3. And we have already seen that there are 3 partitions of 6 into 3 parts. So this may be helpful to reduce n when it's hard. Okay. Thank you for listening. Thank you for tolerating those distinct parts, indistinct parts, and so on and so forth. I believe that they were a bit weird. Anyway, they were important to qualify a distribution. Okay, the kind of distributions we are interested in counting. Thank you very much for following, and I will come back with different topics. Okay.